Hello everybody, welcome to my presentation. My name is Mohammad Partohaghigh. I am a PhD student in University of California, Merced. I am advised by Professor YangQuan Chen and Professor Roummel Marshall. Today I'm going to talk about tail index awareness in fractional order stochastic gradient descent method. Uh, First, I start my work by introducing fractional calculus. In fact, fractional calculus expands classical calculus by extending derivatives and integrals to non-integer order or fractional orders. There are lots of um, fraction operators to find the fractional derivative of a function, but the most important operators are Riemann-Liouville fractional derivative and Caputo fractional derivative. As for a given function, the fractional order derivative of the function with the order of alpha is as follows. Here you see that both definitions contain an integral term. The difference here is that you see that so for the capital fractional derivative, the integer order derivative of the function is inside the integral, but for the Riemann-Liouville derivative, we have the derivative of whole integral. Okay, and here you see that alpha is between n minus 1 and n when n is an integer number. Uh, One of the properties of fractional calculus here is that, in fact, fractional calculus captures memory and non-local effects. And also, the fractional order alpha here interpolates between function and its derivatives. One of the applications of fractional calculus is modeling complex systems in physics, engineering, finance, and machine learning. Uh, today, we have a fractional order gradient descent method to talk about. But first, we have an integer order fractional. We have an integer order stochastic gradient descent as follows. You see that its update rule is as follows. And here, eta is the learning rate and L is the loss function. It has many applications in deep neural networks, larger scale optimizations, and the like. One of the weaknesses of integer order stochastic gradient descent method is that it ignores historical memory of the gradients. In fact, each update depends only on the current gradient. Also, sometimes it converges slowly and or it get trapped in a sharp local minima in complex loss landscapes. So, motivating by this fact, so we introduce a new type of stochastic gradient descent method, uh, which is called fractional order stochastic gradient descent. So, in fact, it extends a traditional SGD by using fractional order calculus to improve convergence and robustness. The key idea here is that we replace integer order derivative by fractional order derivative. Uh, uh, Here, in the update rule, in order to have, instead of having an integer order gradient, okay, we use a fractional order gradient. Uh, so in which alpha is a fractional order and here eta is the learning rate. The advantage of this formula is that so it captures a memory effect. Okay. Also, we have a faster convergence in complex optimization landscapes. But there's a challenge here. In fact, finding the optimal alpha is a big challenge. So we need to find a way to find the optimal value for alpha. Also, you see that here finding the optimal learning rate also is a challenge for both integer order and fractional order SGD. So we consider the fractional derivative of the capital type with n is equal to 1. Okay, when n is equal to 1, we have this definition, which inside the integral you see that we have the first order first order derivative of the given function. Also, alpha is between 0 and 1. Uh, as I said, alpha is a fractional order that controls memory influence, and also here 1 over gamma of 1 minus alpha normalizes the integral. Okay, so the capital derivative here enables a fractional order SGD to leverage past gradients for stabilization in optimization. Okay, so now we have this update for fractional order SGD, but by using Taylor series for the fractional gradient, we get relation 3, and also we consider the learning rate as mu naught over square root of t, okay, which mu naught is a learning rate, and also delta here is the stabilizing constant. So now the goal here is that to find best alpha and the best mu naught. So what is the idea? Suppose we have a data set with k classes, okay, in which m largest is the sample count of the most frequent classes, and m smallest is the desired count for the least frequent class. Okay, we define a new imbalance ratio as m rho is equal to m largest over m smallest. The goal is that to gradually decrease class sizes from m largest to m smallest. Now here we introduce a decay factor as lambda, which is between 0 and 1, as follows. We consider lambda to the power k minus 1 is equal to m smallest over m largest. So from here, lambda is equal to rho to the power negative 1 over k minus 1. So using the lambda from the previous step, we define the target size for each class, okay, as the follower function of m largest times lambda to the power I. So in fact, here we have exponential decay in sample count over classes. So how to find the best alpha? In fact, from the previous uh, new data set, okay, with class sizes mi, okay, in order to find the best alpha, first we define a set of fractional orders, okay, then we run fractional order SGD for each alpha over each k data set indexes. After that, we evaluate the final test accuracy for each configuration, and at the end, we select optimal alpha, which is achieving highest test accuracy. So after that, after finding the best fractional order, we fix fractional order for fractional order SGD. Then we use that fractional order to find the best learning rate. Again, we define a set M for learning rates, okay? Also, after that, we train a model with fractional order SGD on an imbalanced data set for each mu naught in the set of M. By doing this, we can record the final test accuracy for each pair of index and mu naught, and at the end, we select the mu naught yielding to the highest test accuracy. So by doing this, we get the optimal learning rate, I mean mu naught. So Uh, we do an experiment here on the MNIST data set, on the imbalanced MNIST data set. We set um, um, fractional orders as follows from 0.6 to 0.99, and also we consider the set of learning rates as 0.001 to 0.5. So now we run fractional order SGD first on the uh, set of fractional orders. So here you see that for each index, we get different values of fractional orders. For example, for the first index, we have the best fractional order as 0.99. For the index of 5, we have the same value also for index 6. And also for index 9 and 10, we have the same optimal value for fractional order. Here you see that for the index 7, we have the fractional order as 0.9 as the best fractional order. Also, for each index, we have the best test accuracy. Okay, here you see that for the index 7, we have the lowest test accuracy, and for uh, index 5, we have the highest test accuracy. So the graph of the test accuracy over fractional order, here you see that we have an increasing trend for test accuracy over each alpha. Here you see that alpha is equal to 0.99 has the best performance compared to the other fractional orders. Also in this figure, you see that for all of the indexes, okay, we have this trend of test accuracy for each alpha. You see that for we have an increasing trend again for each alpha. Uh, you see that in most cases, 0.99 has the highest test accuracy. So now we have obtained that we have concluded that alpha 0.99 is the best fractional order. And now we use this obtained fractional order to find the best learning rate. So here you see that the best learning rate among other learning rates is 0.5. Okay, here you see that the best test accuracy is for learning rate 0.5. So we can conclude that the fractional order 0.99 and learning rate 0.1 are the best options to the fractional order SGD. So here you see that we have established a systematic approach for tuning fractional order and for fractional order SGD on the imbalanced data set. And also you see that the outcome of this work is the two-stage optimization framework ensures that both parameters are jointly tuned for improved convergence, stability, and generalization in fractional order SGD. Thank you so much for your attention.